The dead technology fought back. By 1959, the transistor was supposed to bury the vacuum tube forever. It was smaller, cooler, tougher, and promised a future without glowing glass bottles burning inside radios, televisions, and computers. But RCA, one of the most powerful electronics companies on Earth, refused to accept the obituary. It built a tiny metal tube barely half an inch tall and claimed it could challenge the transistor on size, power, reliability, and performance. They called it the NuVistor. For a moment, it worked. Defense buyers wanted it. Television makers used it. Audio engineers respected it. RCA sold more than 2 million units by 1962. Then came the trap. RCA had not built the future. It had built the perfect distraction. Vacuum tubes began with a strange observation from the late 1800s. Electric current could cross empty space inside a sealed bulb, before scientists even had a name for electrons. That name arrived in 1897, when J. Thomson identified the electron at Cambridge. Thomas Edison stumbled into the next clue while improving incandescent lamps. His bulbs heated carbon or tungsten filaments until they glowed, and a metal plate inside the bulb could draw current in one direction. Edison patented the effect, gave history his name again, and then left the idea mostly unused. Others saw the weapon. In 1904, John A. Fleming turned that effect into the first thermionic tube. It used a heated cathode to release electrons and an anode to collect them, creating a diode that could rectify radio signals. A one-way gate had arrived. Then Lee DeForest added the missing piece, a wire mesh between cathode and anode. This control grid could restrain or encourage electron flow, turning the tube into both a switch and an amplifier. That changed communications. AT&T understood immediately. Better amplifiers meant clearer long-distance telephone calls, so it bought DeForest's patent and handed the unreliable design to Western Electric. Western Electric improved the vacuum, changed filament materials, strengthened the internal structure, and made the device practical. The fragile experiment became infrastructure. For the next 50 years, tubes ruled electronics, but their weaknesses never disappeared. They were bulky, fragile, hot, and hungry for power. In practice, they behaved like specialized light bulbs, and thermal stress could break them without warning. ENIAC showed the nightmare. The famous computer used more than 17,000 vacuum tubes, and when one failed, operators had to hunt for the dead part inside a maze of hardware. That was progress with a fever. RCA sat near the center of this world. Founded in 1919, the Radio Corporation of America was created after pressure to transfer critical radio communication patents from British Marconi into an American-controlled company. Patents from GE, Westinghouse, United Fruit, AT&T, and others joined the pool. Their representatives sat on RCA's board. At first, RCA was less a manufacturer than a patent fortress. GE and Westinghouse made much of the equipment, while RCA distributed products and collected fees from radio-related patents. The toll was steep. Independent radio makers paid licensing fees around 7.5% of gross sales and were pressured to use RCA parts, including its vacuum tubes. Then, regulators struck. In 1931, a judge ruled that RCA's exclusive tube contracts violated antitrust rules against tying. By 1932, GE, Westinghouse, and others had to sell their shares and leave the board, giving RCA independence. But RCA was already becoming something bigger than a patent pool. It was becoming a machine. David Sarnoff saw radio as more than ship-to-ship communication. He imagined a radio music box delivering music, news, and sports into homes, then built the ecosystem to make that future real. RCA became vertically integrated. It owned broadcasting power, media reach, manufacturing capacity, and a growing research machine. Licensing revenue helped fund new fields, especially television. the patent vault exploded. RCA held 1,183 patents in 1929. By 1944, it controlled 8,258, most created internally. Tubes remained the cash engine. Even after licensees were no longer forced to buy RCA tubes, replacement tubes for radios and televisions produced rich margins. By the early 1950s, RCA controlled about 25% of the global vacuum tube market. Then, Bell Labs detonated the future. In mid-1948, AT&T's Bell Labs announced the transistor. Writers quickly described it as a tiny solid-state substitute for the vacuum tube, capable of amplification, without blasts, heat, or glowing filaments. The threat was obvious. RCA moved fast. Its teams licensed AT&T patents, repeated the experiments, studied the physics, and began generating transistor patents of their own. But inside the labs, one fact became clear. The transistor was revolutionary. It was not ready. The first version, the point contact transistor, used two extremely fine wires barely touching germanium. It was historic, but delicate. Western Electric improved manufacturing with a smaller protected package. Yet random failures still happened when tiny contacts separated from the semiconductor. New junction transistors were sturdier. They used layers of differently doped germanium or silicon to move charge carriers, but manufacturing remained difficult. The numbers told the truth. In 1953, 5 years after the Bell Labs announcement, Western Electric and Raytheon together produced only about 50,000 transistors per month, across 12 variants each. In 1956, semiconductor companies sold 12.5 million transistors. That sounds huge, but the same year, 474 million vacuum tubes were sold. Tubes also handled demanding jobs transistors could not yet dominate, especially high-power microwave and radio frequency applications. So RCA saw danger, but not extinction. And that is where the story turns. What do you do when the future is real, but the present still pays? RCA chose a two-front war. On one front, it kept investing in solid-state research. On the other, it pushed vacuum tubes into territories where early semiconductors were weak. Materials science gave tubes new life. High-temperature ceramics, stronger mechanical structures, and vapor or water cooling made them tougher under heat, shock, and vibration. Designers also used parallelism. Instead of one large cathode grid anode structure, they packed many smaller structures into a single tube, improving high-frequency performance. The supposed dying technology boomed. Between 1958 and 1962, RCA alone introduced 800 new tube models. Then, in 1959, it revealed its boldest answer to the transistor, the NuVistor. It looked less like the past than a warning from the future. RCA said the name combined nueva, meaning new, and vista, meaning prospect. Marketing aside, the device still used thermionic emission, the same basic principle as earlier tubes. The difference was execution. A NuVistor stood about half an inch tall, roughly thimble-sized, small enough to mount on a circuit board like a transistor. RCA removed glass and mica, replacing them with a metal body and solid ceramic base. That mattered. Glass could crack under heat. The NuVistor's electrodes were fixed at one end in a cantilever structure, improving resistance to shock, vibration, and thermal stress. Its assembly was strange and precise. Components were loaded upside down into a jig, moved through a high-temperature brazing furnace, joined by melted filler metal, fitted with a cathode cup, sealed in an outer envelope, evacuated, and finished under vacuum. The 7586 in March 1959. 7 more followed, including the RCA 7262 and 7263, which were developed with military sponsorship. The small tube found real customers. By 1962, RCA said it had made and sold more than 2 million NuVistors. Division Vice President John Farese claimed demand was so strong that RCA had produced over 1 million units in the previous 5.5 months. Defense buyers liked its ruggedness. NuVistors appeared in sonar. airborne weather radar, satellites, and test equipment. They performed well in low noise, very high frequency, and ultra-high frequency applications. RCA also used them in 1960s color televisions, where they helped strengthen picture performance and reduce noise and snow. High-end audio adopted them too, especially in FM tuners, tape recorders, and microphones. For a dying technology, the corpse was busy. 2 million units sounded impressive until compared with hundreds of millions of tubes sold annually. Meanwhile, transistor sales were rising 3 to 4 times year over year. Price made the gap worse. RCA quoted a distributor resale price of $480 for the 7262, about $5,500 today. The higher grade 7263 was quoted at $690, about $7,900 today. Transistors were moving the other way. In 1958, Fairchild sold silicon transistors for about $150 each, and that was the highest price they would ever see. The curve had turned. RCA continued narrowing its tube strategy. After the NuVistor, it pushed Sermalox power tubes for high-power RF amplification, the kind needed to send signals across long distances. RCA later noted that a Sermalox tube flew inside NASA's Pioneer 5 Venus probe. Specialty tubes still had a future, but RCA's broader business model was cracking underneath. RCA had long depended on patents. It did not simply license a few key inventions. It bundled large pools together, forcing companies to take patents they did not necessarily want. Regulators saw another tying problem. In 1958, RCA settled a consent decree that made domestic companies, including Zenith, able to license RCA patents royalty-free. Yet foreign licensees still paid, so RCA licensed technology to at least 82 Japanese companies and later to a Taiwanese research institute. That decision helped future competitors. RCA never became in semiconductors what it had been in tubes. Texas Instruments built the first commercial silicon transistor, a grown junction device. Silicon narrowed the NuVistor's advantage, and integrated circuits pushed costs lower. The NuVistor disappeared in the early 1970s, but the disappearance was not sudden. It was slower, stranger, and more painful than a simple failure. RCA's labs drifted toward defense work, which supplied as much as 75% of lab revenue by the late 1950s. Its factories struggled with silicon lines, while researchers pursued advanced niches like gallium arsenide. Then RCA diversified wildly. Starting with Random House in 1965, it bought publishing, frozen food, car rental, real estate, and carpet businesses. That was not focus. That was escape. The vacuum tube did not die. It survived in radar, microwave, broadcast, and other high-power systems. But the transistor did something larger than replace the tube. It created portable electronics, digital computers, and markets RCA failed to imagine. The dangerous moment is not when an old technology becomes useless. It is when it remains useful enough to defend. The NuVistor was not foolish. It was elegant, rugged, and commercially real. That made it more dangerous, because a bad product warns you quickly. A good product in a collapsing market can keep you busy while the future compounds somewhere else. RCA saw the threat clearly, but brilliance aimed at the wrong future becomes a trap. RCA did not lose because it failed to understand the transistor. It lost because it understood the transistor and still chose to keep the past alive.